Today on How It's Made. Railway bridge ties. Membrane filters. Hydraulic post drivers. And biplanes. The deck of a railway bridge is typically built of wood timbers called bridge ties. They're bolted to steel support beams, located on concrete piers over the water or gully below. The rails on which the train travels are bolted to the wooden ties. Wood absorbs the noise and vibration of the passing train. The load the railway bridge will carry determines the size of its ties. To calculate the load, engineers factor in the number of tracks, volume of traffic, weight of the transported cargo, and whether the bridge is straight or curved. A curve will put additional stress on the structure. The wood of choice is oak because it's hard and strong. When the logs arrive at the sawmill, they come face to face with a menacing-looking device called a debarker. A conveyor moves the shipment toward the debarker, then drops a single log in front of it onto spinning rollers. The rollers rotate the log, while the debarker makes its way from one end to the other. It chews off the bark with its sharp-toothed blades. What the debarker shaves off is put to good use. The bark gets processed into gardening mulch, and they burn the sawdust in the wood-fired boiler that runs another part of the plant. Next, one log at a time drops into a mobile carriage that runs it through a circular saw. The carriage has sensors which detect the log's extremities and report its dimensions to a console located in the operator's cab. The operator interprets the data. Using a joystick controller, he flips the log into whichever position maximizes the yield. The first few runs trim off the rough surface and square the shape. The next runs cut boards, which the sawmill sells to flooring plants. This continues until the log is the exact dimensions of the bridge tie. Again, nothing is wasted. The sawmill processes the cutoffs into wood chips, which it then sells to companies that make particle board, strand board, and similar construction materials. The sawmill stacks the ties for transfer to the bridge mill next door. The role of the bridge mill is to frame the bridge, also known as dapping. That's the process of making the specific holes and notches in each tie for attaching it to the steel beam on which it will sit. At the bridge mill, the bridge layout supervisor processes one tie at a time. He carefully reviews the engineer's blueprints, which assign a number to each and every tie. These numbers specify precisely where the saw has to cut notches and where the drill has to bore holes. The locations of these notches and holes vary depending on the tie's position on the bridge, so he must follow the blueprints meticulously. After measuring and marking it all out, he sends the tie to the dap saw. The operator sets up each cut, lining up the mark with laser lights, which indicate the location and the cutting depth of the blade. The notches are just the right size to fit over the steel beam on which the tie will lie. Next, a worker using a drill press bores holes for hook bolts, which go through the tie to secure it onto the steel beams. Each tie receives a metal identification tag, which includes the bridge and tie numbers. On each end, workers nail on a mesh plate made of rust-proof galvanized steel. The plate has teeth designed to grasp and hold together the wood fiber to prevent the end from splitting. After nailing the ID tag to one of the end plates, workers force in both plates with a press. The tie's last stop is the adjacent treatment plant. They spend 24 hours inside a high-temperature, high-pressure chamber, which penetrates them with a creosote borate solution. This protects the wood from rot and insect damage, and extends the tie's lifespan from about a decade to at least 25 years. When filtering liquids, it's all about thinking small. Membrane filters can separate the tiniest solids from fluids, which purifies the liquids and recovers the solids. Once separated, the two substances may then be reused, so that nothing goes to waste. Membrane filters can turn murky water clear, almost magically. To demonstrate, a technician installs a spiral wound membrane in the housing of a pumping system, which is a small-scale version of what you would see in a factory. She turns on the tap and water flows into a tank. She adds latex paint to purposely sully the water. The system pumps the contaminated water through a strainer, and then the membrane filter, while meters measure the flow. Within minutes, the paint has been filtered out, and the water is clear. The making of a membrane filter begins with polypropylene mesh. An automated system unwinds the mesh and cuts it to length. These mesh sheets will be used as spacers. They'll create gaps for the liquid to flow through the filter and over the membrane. Next, the system cuts sheets of polyester fabric. These will form channels through which the filtered material will travel. These sheets are known as permeate spacers. An employee stacks the polyester fabric sheets. Using high-frequency sound waves, she welds one sheet to the next at just one end. She layers and welds a total of 15 sheets and then applies double-sided tape. The tape is for attaching the packet to a central tube, and it will also serve as a guide to correctly align it. Next, the membrane soup flows into a long trough. It's a mix of melted plastics and solvents. Paper backing unwinds into the trough and is coated with the soup on one side. The coated paper then travels through 2 quench tanks, and the plastic components solidify as the solvents are drawn out. The exiting solvents create a unique pore structure in the remaining white plastic membrane. The membrane now travels by a light box, which illuminates any visual defects. An applicator also drips a preservative onto the membrane. A team unrolls the membrane onto a work table. They lay a sheet of the polypropylene mesh, which we saw cut to size earlier, on the membrane. The employee then cuts the membrane to twice the length of the mesh. They fold the membrane over the mesh, creating a membrane envelope. The mesh serves as a pathway for fluid to flow between the membranes. Meanwhile, another worker applies epoxy to a perforated plastic tube. He attaches the permeate spacers to it with a double-sided tape, giving the epoxy time to cure for a permanent seal. He and a colleague apply more epoxy to the perimeter of the bottom sheet. They transfer the membrane envelope to it and continue to layer, making a permeate fabric and membrane sandwich. The worker then winds the glued layers snugly to a perforated plastic core, forming the spiral membrane filter. He tapes the multi-layered wad from one end to the other. The tape holds everything tightly in place as the epoxy cures overnight. They leave the tape on after the cure, and the machine winds epoxy-drenched fiberglass rope around the entire filter. As the epoxy cures, the rope will form a hard shell around the membrane filter. Partway through, they apply the label with the company name. The operator captures the glue runoff during the wind. And it's a wrap, so he cuts the rope. From the side, you can see the flow channels between the layers. Concentrated contaminants will travel through them and out. The filtered liquid will seep into the core and exit, clearly improved. The invention of the hydraulic post driver in the 1960s allowed workers to drop their shovels and sledgehammers and let a machine do the job of pounding fence and signposts into the ground. When it comes to labor-saving inventions, this one is definitely a striking example. The post driver raises hefty fence or signposts into position and then slams them into the ground. Inside a vertical case, a hydraulic system drops a 300-pound weight to drive the post and then lifts it for another hit. This machine does the work of 2 or more brawny humans, with just one person at the controls. To make it, they start with a vertical case for the weight. A high-precision plasma torch cuts steel into a rectangular shape and makes holes for components. They insert the rectangle into a brake press repeatedly to bend it into a 3-sided part. The profile includes flanges for welding it to the back wall of the case. He fits the part to the back wall and welds them together, completing the post driver case. An employee builds the post driver weight working within a weld fixture. It's a box-shaped weight, and he welds it at the seams. He taps the corners between the welds to maintain a tight configuration. This 300-pound weight can later be filled with steel shot to make it even heavier for greater impact. The next worker assembles yellow steel jaws to a hub to produce the grapple. This is the part that grips the fence post and raises it into position. He sticks a danger label onto the hub to warn people to stay clear of these powerful jaws. He attaches a hydraulic cylinder, which will make the jaws open and close. He connects the cylinder to the grapple jaw. Next, they move on to the metal plate that will be used to mount the post driver to a vehicle like a skid steer loader. It includes a hydraulic mechanism for tilting the fence post left or right. The employee installs a control valve next to the cylinder and links the two with hoses. He'll also connect the grapple and weight hydraulics to this valve. Back to the post driver case now. It's been painted and they're ready to install the hydraulic motor. The worker connects it to the sprockets and chains that will lift the weight. He pins the sprockets into place and installs tensioning rods on either side. Next, a cover plate protects the sprockets. The tensioning rods protrude through it. He slides springs onto those tensioning rods and compresses the springs to maintain the tension. He now attaches the grapple to the post driver case. He locks it into place with a long pin. He links the grapple hydraulics to the control valve, and it's ready to grab big fence posts and hold on tight. They attach the metal mounting plate to the post driver case. The work table tilts back to move the post driver into an upright position. With the help of a crane, the next worker moves the weight into position and lowers it into the case. He slides a pin into the top end to keep the weight from falling out when the post driver is on an angle. One day in the making, this hydraulic post driver is ready for years of heavy labor, taking over for humans so they don't have to move a muscle. A biplane is a vintage-style aircraft with two pairs of wings, sitting one above the other. The top wings are typically raised above the fuselage, with vertical struts bracing them to the bottom wings. Dating back to the earliest days of aviation, they're still popular for performing aerobatics. A biplane's lower wings have ailerons, which bank the airplane to the right or left. On the plane's tail, elevators pitch the plane's nose up or down, while a rudder steers it left or right. A propeller provides the propulsion. The plane has 4 wings. Each wing has 2 spars, wooden beams at the front and rear, which form the perimeter structure. A craftsman skillfully fashions these spars out of Sitka spruce. This wood is exceedingly light, yet exceptionally strong, making it one of only a few woods approved for structural use in airplanes. After sawing the wood to the spar's shape, he mounts attachment plates made of Sitka spruce and mahogany plywood. These are the end struts, steel vertical bars which will connect the upper and lower wings. He finishes the spar by refining its contour, first with a hand plane, then an electric plane. Using strips of Sitka spruce, he constructs 15 structural ribs for each wing. He begins with long strips, which have been soaking in water for a week to make them pliable. He inserts one end into a curved fixture and leaves the strips to dry. When he removes them a couple of days later, they have a permanent aerodynamic curve. He glues 2 curved strips together to form the perimeter of one rib. In between, he glues short diagonal strips called trusses. He reinforces both sides of each intersection with a rectangular piece called a gusset. An assembler mounts the 15 ribs crosswise on the front and rear wing spars, then installs 3 aluminum tubes called compression ribs. These absorb air load hitting the spars, keeping the wooden ribs from flexing under pressure. The craftsman connects the compression ribs with crisscrossing metal rods. After applying more glue to critical areas, he nails an aluminum trim over the front spar and nose of the ribs. This is called the leading edge. It's the first part of the wing to hit the wind, so it takes the brunt of the air load. Finally, he laces reinforcement tape through the ribs in an X pattern. The completed structure now moves to the covering department, where technicians drape it in heat-shrinkable polyester fabric. They cut the fabric to size, glue it to the wing perimeter, and heat the surface with an iron to shrink the fabric until it's taut. Then they stitch over the glued areas with polyester cord. They brush on a chemical which seals the pores of the fabric. This primes the surface to receive a spray coat of polyurethane paint, which is a special formulation designed for aircraft bodies. Technicians construct the fuselage frame out of high-strength steel alloy tubes. They use an electric torch to slightly melt adjoining pieces so they fuse to each other. Because there's no filler metal bonding the pieces, the welds don't add any weight to the structure. After painting the frame, technicians install aluminum floor panels and bulkheads. In the tail, they add lighter weight bulkheads made of mahogany plywood and Sitka spruce. Then it's time to bolt the engine to the front of the fuselage frame. The engine drives a propeller, made of either wood, aluminum, or a composite material. Painted aluminum body panels cover the frame. Technicians install the fuel tank between the front cockpit and the engine. Then they bolt the wings to the fuselage. Vertical steel struts connect and reinforce the two levels of wings, bolting to those attachment plates on the wing spars. Next, technicians mount the painted aluminum ailerons, the tail, with its elevators and rudder made of painted fabric over welded steel, and then the engine cover. They install a windscreen and instrument panel for each cockpit. The front screen can be replaced with a cockpit cover to keep the pilots warm when flying in cold weather. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.